Next, we're going to take a look at logarithmic functions and figure out what their limits are. And first, we're going to take a look at the graphs again, just to see exactly what's going on. So this is log base 4 of x. We can change the base however we want for right now, but I want you to notice that wherever the function value exists, the limit's going to be the same. Again, there's no jumps in the graph. It's what we call continuous. If it were a rope, there would be no break in the rope. So for example, let's look at 4. As x approaches 4, the y value is equal to 1. That's also what it's approaching. So we can go in and change the base, say to base 3 or base, whoops, I just deleted that. We can change it to base 2 if we wanted to. This is going to be true for any logarithmic function. The limit is going to be equal to the function value, provided it exists. Now look, to the left of 0, the graph doesn't exist, right? So there is no function value. And so obviously the limit's not going to exist either. There's nowhere to put a point on the graph. So keep that in mind. The function value has to exist in order for the limit to exist for a logarithmic function. So therefore, for any logarithmic function, if the function value exists, if f of c exists, then the limit as x approaches c of f of x is equal to f of c. In other words, just plug it in. Whatever you get is going to give you your limit. And again, just to kind of summarize where this falls into play, we've talked about the fact that this is true for polynomial functions. All right, and okay, so this is not. All right, let's try this. This is true for polynomials. This is true for logarithmic. This is true for rational, which we'll talk about in a second, exponential and trigonometric. Right now we're focusing on logarithmic, but basically if you plug it in and you get something back for these functions, that means that's going to be the limit. Let's take a look at some examples of what this might look like. So let's say we have, let's do g of x this time. G of x equals log of x minus 2. Okay, so a little bit of a transformation there. Let's say we want to figure out the limit as x approaches, we're going to do 12. Well, because it's a log function, and because it's continuous everywhere, as we saw in the graph, we can just plug in 12 for x and see what we get. So plug it in, 12 minus 2. Now we know since there's no number there, it's log base 10, so it's actually equal to log of 10. If you need to brush up on logs, go back and watch that lesson. That's going to be equal to 1. So therefore the limit as x approaches 12 of f of x is equal to 1. It's simple. Now, had we tried to find, let's use the same function. Let's say we would try to find the limit as x approaches negative 1 of f of x. Well, sorry, g of x. Let's rewrite that to be clear here. This needs to be g as well. Okay. If we try to figure out g of negative 1, okay, it's going to be equal to log, positive 1. Well, it doesn't matter. We'll do negative 1. If we plug in negative 1 minus 2, we get log of negative 3. Okay, so that doesn't exist. You can't take the logarithm base 10 of a negative number. It doesn't work. And so since that is undefined, the limit is going to be undefined as well. So again, it only works when it's actually defined. When it's not defined for a logarithm, the limit's going to be undefined as well. Also could have plugged in 2 and we would have got log of 0. Of course, that doesn't work either. So as long as you plug it in, it works, and that's your limit for logarithms. Next, we are going to take a look at rational functions.